Today, we're going to walk through the PID Tuning tool in the Fidget Control panel for Windows. This tool can help you experimentally determine the best control parameters for your motor or assembly. Open the Fidget Control panel and double-click the Position Controller channel. Switch to the Tuning tab to access the PID Tuner. Before we begin, we need to start by filling in some of the configurations. Click on Defaults to load the default control parameters. These are the values we'll be adjusting in our test. If you have an encoder for position feedback, remember to check the Use Encoder box. If the box is unchecked and you're using a brushless motor, the control loop will use the motor's Hall effect sensors. In most cases, an encoder will have much higher resolution, resulting in smoother control. If you're using a brushed DC motor, this checkbox won't be present since an encoder is your only option. Next, set the rescale factor for your motor. This will cause all other values to be converted into more easily understood units like degrees or rotations. Check the user guide for your motor controller to learn how to calculate your motor's rescale factor. We'll enter a value that rescales everything for the system into degrees. We'll set our velocity limit to 720, meaning the controller will attempt to drive the motor at 720 degrees per second. Our acceleration is now in degrees per second squared. We'll set our acceleration to 3600. Which is 5 times our velocity limit, so the controller will reach this velocity in a fifth of a second. We recommend setting your current limit to 1.1 times the rated current of your motor. This motor is rated for 7 amps, so we'll set the limit to 7.7. We'll ignore the surge current limit for this video, but you can read more about it in the Position Controller API guide. The inductance field will usually fill in automatically when you open the PID tuner. More details about motor inductance can also be found in the Position Controller API guide. Now set the interval. This is the time in seconds between the two position commands in our test. We'll keep it at 2 seconds. The step size sets how far the motor will attempt to move. We'll set it to 360, which is 1 full rotation because of the rescale value we set earlier. You'll notice that each setting is green or red. Red means that the value has been changed, but hasn't been sent to the controller yet. You can send it to the controller by pressing Enter, or by engaging the motor or starting a test. To begin, we'll create a safe starting point for our tests. Set Ki and Kd to 0 for now so we can focus solely on Kp. Kp drives the motor proportional to the error in the system. Error is defined as the difference between the current and expected position. When error in the system is 1 over Kp, the motor will run at 1.0 duty cycle, which is full power. With 0 Ki and Kd, and Kp set to 0.01, this means that as long as the motor is 100 or more degrees away from its target position, it will turn at full power. Likewise, if error is at 50 degrees, it would turn at half power, and so on. Based on this, choose a conservative Kp to begin with. We'll choose a Kp of 0.005 for this setup. Now we have enough properties configured to run a test. Click Test. You should see the motor move forward, and then reverse, and 3 graphs will appear. The first graph shows the motor position over time. The green line is the target position. This will be the final position for the motor for this step. The purple line is the expected position. This is the calculated target for the PID loop based on the acceleration, velocity, and step size you've chosen. The red line is the actual position of the motor. This is the line that will respond to changes as we tune the parameters. And our goal will be to get this line to follow the purple line as closely as possible without causing other problems for our motor. If your acceleration is set too high, the purple line may be steeper than what is physically achievable. The second graph shows the error in the control loop. Error is defined as the difference between the current position and the expected position. Be aware that the error plot may not represent this behavior exactly, due to the way duty cycle and error values are reported by the controller. The third graph is the duty cycle graph, which shows how much power the controller is giving to the motor. 1.0 is full power, 0 is no power, and negative 1.0 is full reverse. Together with the error graph, it can provide insight into what the position controller is trying to do. As you do more test runs, your previous 2 tests will be overlaid in different colors, so you can see what difference your last change made. Now that we have everything set up, we can start changing parameters and running tests. As we increase Kp, the motor tracks the target position more aggressively. If Kp is raised too high, you'll get overshoot or oscillate on the target. Notice how the bar shakes at the end of the step with high KP. KI looks at the error over time and pushes the motor harder the longer the error persists. For example, KI of 0.001 would push the motor to full power when the error is 1000 degrees for 1 second. Similarly, it would contribute 0.5 duty cycle if the error was 500 degrees for 1 second, or 1000 degrees for half a second. You can see that without KI, our motor is struggling to hold the weight of the bar horizontal against gravity. With a bit of KI, we can solve this problem. KI gradually increases motor power until it is balanced with the downward pull of gravity. KD is different because it works against KP and KI, dampening the drive towards the target. This can be used to reduce overshoot. Because this position controller uses a trapezoidal control algorithm, KD is not as effective as in classical PID control. Adding too much can cause the motor to vibrate in place loudly. So if you decide to add KD, you should start several decimal places lower than your KP and work your way up slowly. If your system has overshoot, you may find that lowering KP gives better results than adding any KD at all. So continue to use the tool and make adjustments until you're happy with the motor's response. One final parameter to discuss is the deadband. Adding deadband creates a buffer zone around the target position. This means your final position will be less accurate, but setting a deadband can help if you find the motor is vibrating or oscillating when it reaches the target position. You can't use deadband in applications like this one, where the motor needs to hold a load while at rest, because the motor will disengage once it reaches the deadband, causing it to get caught in a loop of disengaging, slipping, and then jumping back into place. Once you're finished tuning, you can click Save to save the parameters to a file that can be loaded next time. This concludes the walkthrough of the Fidget Control Panel PID Tuner. For more information, see the PositionController API Guide and the Quick Start Guide for your controller, both of which can be found on the product page for your Fidget.